This work, I work for one century project supported by FNR. And I think this is a purely core project focused on academic output to this project. And we are trying to also find some use case to apply our technology, to apply our research development for trying to find some opportunity and to benefit the existing startup. So this is my work. I can share with you friendly about the semantic augmentation. I'm the first one to apply to the Earth observation. And this Earth observation provides to process the onboard processing on the satellite and collaborate with a nearby satellite to perform a cognitive semantic augmentation, which can improve the recognition of the neural network on onboard processing on the satellite. So that is the recent work I provide to this research. And I provide a new term of cognitive semantic augmentation, which is starting motivated from the two very interesting research idea about the deep joint source channel coding. And in the meantime, there's another new idea about the semantic augmentation or semantic communication. We generally using this word and trying to think about a new way of digital communication to apply as we know, the advent of the machine learning, apply the neural network. We can rethink about the way to communicate using in human-like way to perform this semantic communication. So as our human communication, we use the language to communicate with each other. So if we apply this kind of idea into the digital communication, there's a new ambition for this idea for semantic communication, which will try to outperform the channel bound of all kinds of communication theory. So that is the real ambition about semantic communication. So I'm trying to do some research and trying to do some survey on this round of field, and I'm doing my best to trying to find a new interesting study I'd like to share with you. So in this study, I would like to contribute a first one end-to-end semantic augmented communication process, which is what I would like to catch in you. If you have some study in the machine learning, you must heard about federated learning. So I would like to perform this new idea and using the cognitive semantic augmentation. I'm trying to use this approach to outperforming the federated learning. It is famous. It's a famous machine learning announced by Google. So using this kind of communication, the neural network can learn from the source using joint source channel coding, and then provide some new way to communication. Apart from the digital communication, we're using the deep joint source channel coding to transmit this digital data, and using digital modulation to transmit on the channel. And we training the receiver using the same way of neural network to recover or to recognize different kind of source using this joint combining source and channel coding together. And also I combine with the new idea published in the Journal of Image Processing, is using the concept of using the concept of the semantic augmentation, is apart from the image level. Apart from the image level, the image level of augmentation is not quite easily to let neural network to adapt to the new source, and it is very easy to get distortion from the image level augmentation. So if we use different kind of idea about the semantic recognition from the image source, we will let neural network to learn better from the image source, and trying to train the neural network about the semantic meaningful representation. So in this kind of way, if we consider more detailedly about the semantic augmentation, it will provide some gain to neural network and improve a certain level of performance to the neural network. So first of all, I would like to introduce the digital task-oriented joint source channel coding. Is quite communication-oriented of joint source channel coding, because it considers the digital modulation to transmit on the channel. As we familiar with the wireless channel, we can use this kind of deep task-oriented joint source channel coding, because at the very beginning, this research focused on the two kinds of way we can consider. If the neural network can have the access to the image data or source data, they will have more ability to learn from the data, because during the transmission, you're always based on some task. I will give more example for the next slide. So this is task-oriented for the neural network machine learning. We can think about when we trying to do some task. Based on the task, we can focus on the information what we need. So if we train the neural network based on this kind of approach, we can gain some meaningful compression from the source data, and then provide more source data to protect our transmission message and provide a more robust solution. That is the whole spirit of DT-JSCC approach we would like to provide you. So based on this idea, we were trying to train the neural network in different task-oriented approach. And then this kind of task-oriented approach, we can have more efficient digital communication. So in detailly, we can consider a very simple neural network, CNN, in the transmitter and the receiver. And then we can apply the quantization, a very common quantization used in the neural network. So after quantization, we will get the corresponding learnable codebook. So using this codebook, we will transmit this codebook and instruct from the neural network, we can transmit through the channel. And based on the loss function, we can achieve a better new way of capacity we can provide for the semantic communication. So that is the, I think this is the most feasible way for us to implement a not very complicated semantic communication, because this is only a very simple convolutional neural network. We don't need to use a very complicated neural network for understanding the semantic of the source data. We only use to catch the feature from the source and then transmit those features and to perform the learnable codebook and transmit using digital modulation from the channel. And then after the receiver will recognize and recover those tasks we are going to perform. So next, I'm going to introduce this very interesting technology philosophy for the semantic data augmentation. We can see that if we focus on different tasks, we see there's the two tasks I am going to provide and show to you is for this bird image, this task, if we focus training the neural network to the landing task to build this Arctic tern, the neural network can learn the meaningful semantic direction from the spreading wing, eating, or bowing head for this bird image. So the neural network is able to discriminate and to lower the weighting about the meaningless semantic direction, which will protect us, provide us a new way to let neural network to less being destroyed by the noise. So the fine-grained part will be able to prevent the shortage disadvantage from the image data augmentation. It's very easy to get distorted by some damage from the fine-grained detail. It will let the neural network to confuse between these three images being transformed from the digital transformation. So neural network very easily confused by if we consider in the image level domain of this image will directly transform mapping to the outer of the categorized domain we can see in the red circle. So if we consider in the semantic data augmentation in different tasks, the neural network can learn the new meaningful semantic direction. For example, in this task, we change to flying, and then we can see the neural network easily to learn from this learnable semantic meaningful direction for landing, fishing, and diving. So as long as we get some transformation from the fine-grained detail, as long as the neural network has been trained to learn the semantic meaningful direction, we are able to provide more higher prediction accuracy using this semantic data augmentation technique. So I would like to use this kind of technology applying to onboard processing and provide a new idea about the cognitive semantic augmentation. So based on this technology, we also can use the traditional convolutional network we recognize as a backward propagation to update the parameter of feature extractor. And also, the most important feature about the covariance prediction network used to provide the semantic meaningful understanding recognition for the neural network to provide the more accuracy parameter, not only the feature extractor and also the parameter in the covariance prediction network. So the backward propagation and the backward propagation will use to optimize this neural network and provide a better prediction performance for the Earth observation as well. So I bring up this idea to build these two satellites. If one satellite one observes some image from Earth, from satellite one, it uses DT-JSCC transmission to the satellite 2. And using a satellite 2 embedded a new powerful way to understanding the semantic data augmentation, it will trying to train his neural network on board on the satellite 2 and provide a more optimized parameter in the neural network on board on the Earth observation satellite 2, it will provide a more accurate Earth observation prediction and provide a more accurate transmission to the receiver. So based on this idea, I combine this very important approach, and then we can achieve this new technology term. I provide this new invention to name as the cognitive semantic augmentation, and apply to the Earth observation satellite. We can do some wireless channel experiment. We would like to see and make some comparison with the famous federal learning. So we can have some initial result we can see from the DT-JSCC using the 16 APSK modulation and applying on Russian, relay, and ALGN channel. To see the performance when we're using the DT-JSCC, we can observe using the Euroset data set to see how much it can achieve the performance from PSNR 2.5 to 20. And the most important of all, we are very exciting to see this improvement from our cognitive semantic augmentation technology. We can outperforming the federal learning at high PSNR because the low SNR are being distorted by the channel. So after we have some, even we have some recognition improvement from the covariance prediction network, but the source image has been distorted by the channel severely. So we have very poor performance. But after that, surprisingly, in the middle of the PSNR, we can see outperformance very quickly comparing to the federal learning. When we just transmitted the parameter from client to the server, our cognitive semantic augmentation can have better recognition for the top 1 accuracy. So that's a very interesting result. We would like to inspire you in this room or online. We can see that in using this artificial intelligence neural network, we can achieve a better digital communication for the semantic communication. So the most important feature for this approach is we are comparing with 100 iteration round between the server and client of using federal learning. Our approach, cognitive semantic augmentation, only use 1 transmission end-to-end. It will perform better than the 100 round federal learning. That is the most important contribution I would like to present to you. So I would like to thank you for your attention for today's meeting and talk, and I'm finished at this moment. I hope the time is just right, and if you have any question, I would like to discuss and answer to you. Yes, I think you're asking a very good question because for this result, I only do myself, and then you provide me a very good a question about the multi-pass channel to consider in the intersatellite link. So I only consider a very simple case, just a direct transmit. Yeah. I am very happy to study more around this field, around this approach to consider the multipass channel. Yeah, to see any kind of difference or any performance gain we can gain comparing with the conventional 6G satellite system. Yeah, if you don't have any question, or you can discuss with me offline about the European life, I would like to have a very short chat with you. Yeah, I'm freely after the afternoon. Yeah, and so feel free to come to me and I will answer you every question you have. Thank you. Thank you so much.